So I'm going to start our discussion on port parameters by using what are called the Z parameters or the impedance parameters. And these parameters are based on a relationship between voltage and current and are really just an expression of Ohm's law. I'll preface this discussion by saying we don't really use Z parameters in application very frequently. They are most often used as a learning tool so that you can just kind of understand the application of port parameters. So I'm going to show you how to use these Z parameters, where they come from. We're going to do an example of using them, but mostly that's a learning method just so that you get familiar with the utilization of port parameters, and so that when we get to more complex mathematical analysis, you kind of understand the point. So let's get to it. The most basic port parameters that we have are these Z parameters, or again, they're called the impedance parameters. Z is impedance, and they relate voltage to current. And I'm going to write what they mean. So you see we've got a two-port network, and we've got a voltage across port 1 and a current into port 1, and we've got a voltage across port 2 and a current out of port 2. So we can write a matrix representation of the relationship of V1 and I1 to V2 and I2 through this network. And that is going to be V1 and V2 as the first elements of our 1x2 matrix, and that is equal to the port parameter matrix Z, which consists of 4 elements: Z11, Z12, Z21, and Z22, times I1, I2. And if you're not familiar with matrix notations of systems of equations, what this is this is a two equations with two unknowns, and these quantities are known. So we've got V1 equals Z11 times I1, so V1 equals Z11 times I1 plus Z12 times I2. The second equation is that V2 is equal to Z21 times I1 plus Z22 times I2. So these are equivalent ways of writing the same thing. It is not obvious why we do this, since we're just doing two-port networks. In multi-port networks where there's many ports, it's much easier to write these matrix representations than it is algebraic equations. Additionally, this is how you would write it in a computer if you were solving it, right? Computers don't typically understand this, but many computer programs understand matrix operations. So commonly this is simplified to just say that the voltage at all the ports is equal to the port parameter matrix times the current at the ports, right? And this would be the matrix analysis. So what about these Z parameters? What are they? Well, clearly they're a relationship between voltage and current, right? We could just divide this. And so the relationship between voltage to current is just impedance. Well, there's 4 of them, so let's talk about exactly what each of them mean. Z parameters are the ratio of voltage to current when the driving port of the two-port network J with current IJ, and we open circuit the other ports and we measure a voltage at port I. So that's kind of a mouthful. I'll write it in mathematical form and then we'll do some examples. So we've got the port parameter, impedance parameter Z sub ij, is equal to the voltage at port I divided by a current that's injected into port J when all other ports in the network are open circuited. So that's a key to this, is all other ports. So IK equals 0, meaning there's no current flow, for K not equal to J. So we're just saying we open circuit all the ports. So I think that this is best understood by performing an example, but first I'm just going to represent what a couple of the ports mean. So let's take a look at Z11. If we've got a two-port network, Z11 is going to be V1 over I1. So we want to take the ratio of V1 to I1 when everything else in the circuit is open circuited. So what we're doing is we're inserting a current I1 into port 1. This is our 2-port network. It's got an output port. It's got our input port, and V1 is this right here. So we just need to find out what the ratio of V1 to I1 is under this condition. And that gives us Z11. Well, what about Z21? That's the ratio of V2 to I1. That's the injecting current. So it's that same circuit, I1, that's a current source right there. We've again got our 2-port network Z here, but now we want to know what the output voltage is, V2, and that would give us Z21 if we divided V2 by I1. So let's do a numerical example of that, because I think it helps explain things. So let's take a network, a very simple network of some resistors. We've got a 10 ohm resistor. Here is a 30 ohm resistor, and here is a 60 ohm resistor. And to structure that as a 2-port network, we've got port 1 here and port 2 here. Strictly speaking, you don't need to have a box around it to make it a network, but I'll just put one there so that it's a little more clear. So there we go. That's our 2-port network. So what we want to do is now determine what all of these network parameters are. So I'm going to start at Z11, which remember is just V1 to I1 with all other ports open circuited. So I'm injecting a current into port 1. It's going into this network here. Right? And that's I1, and I'm measuring the input voltage, V1, right? And so this is an ideal current source. There's no voltage drop across an ideal current source. So I can just write that for this network, V1 is equal to I1 times the Thevenin equivalency circuit here. And remember, this is 10, 30, 60. So I'm just using some basic network analysis tools or skills to figure this out. Ohm's law, Thevenin equivalency, and so that's I1 times whatever the combination of 10 ohms in parallel with these two series elements are, 30 plus 60. So series combination, parallel combination. So that's 10 times 90 over 10 plus 90, and that gives me 9. So V1 in this orientation is equal to I1 times 9, which means the port parameter Z11 is equal to 9. So that's the calculation of Z11 for this network. So now let's move on to calculating Z12. Z12 is equal to the ratio of V1 to I2. So we got to change what port is the driving current in this one. So we've got 10 ohms, we've got 30 ohms, and again we have 60 ohms. So that's our network. We need to measure V1, which remember is the voltage across port 1. And then we need to inject I2 into port 2. So this one, the network analysis technique, is a little bit tougher. The general technique that I'm going to use is that I can determine the voltage at this port right here, that's V2, and I can use the voltage divider between the 30 ohm and the 10 ohm to determine what V1 is measured here. So that's the technique I'm going to use. It's not the only way to solve for V1, but it's just the one that I'm choosing to use. And so in this case, V2 is equal to I2 times 60 ohms in parallel with the 30 and 10 ohm series combination. So that is 40 ohms right there. And so that is, I can divide both sides by I2. I get V2 over I2 is equal to 60 times 40 over 60 plus 40, is equal to 24. So that's the voltage right here. To determine the voltage here, I've got a voltage divider set up between the 30 and the 10 ohms there. So I can say V1 is equal to 10 times V2 over 30 plus 10. So that gives me V1 is equal to V2 over 4. And I can rearrange that and I can say 4V1 is equal to V2. So I can put 4V1 in right here and I get 4V1 divided by I2 is equal to 24. I divide both sides by 4. I get V1 over I2 for this circuit is equal to 6. So that gives me the Z12 parameter. Next, I need to determine Z21. And the Z21 parameter is defined as V2 over I1. So we are injecting current into port 1. And we've got that same resistor network, 10 ohms, 30 ohms, 60 ohms, and this time we need to measure the output voltage plus minus V2. So this one, I'm going to use a similar technique. I can determine what the output voltage here is, again, by a voltage divider. So I can just say that V2 here is equal to 60 times the voltage at that node, which is V1, divided by the two legs of the voltage divider, 30 plus 60, and that gives me V2 is equal to 2/3 V1, or V1 is equal to 3/2 V2, just by rearranging that fraction right there. So what I'm going to do is, if you notice, this circuit here is the same as this circuit here, so I'm just going to use this this equation right here and just plug in for the relationship I just solved right there. So I've got V1 equals 9I1, and in that same circuit I can just put in 3/2. V2 is equal to 9I1, and then I can solve for V2 over I1, and it gives me the value of 6. So that gives me my third of the impedance parameters. And finally, I need to analyze Z22, which is just V2 over I2. So what I'm doing here is I've got my 10 ohm resistor, 30 ohm resistor, 60 ohm resistor. I'm injecting current at port 2, and I'm measuring the voltage at port 2, V2. So interestingly, I've already done this analysis. I solved it right here when I solved for V2 to I2, so I don't have to repeat that. I can just use this same math to say V2 over I2 is 24. So that is the fourth network parameter there for the impedance parameter. So if I were to write my matrix math, I would write V1 over V2 is equal to the port parameters, which are Z11, Z12, Z21, and Z22. Then I multiply those by the currents. So if I know either the input voltage and the output voltage, or the input current and the output current, I can calculate the other based on the Z parameters. So now we can completely relate voltage and current waveforms at the two ports of the network. In this case, it's not super useful. It probably would have been easier to just use a standard network analysis technique, since we're just looking at a resistive network right here. But this technique is often used to characterize more complicated electrical networks when we don't really know what's going on here, but we do have access to the ports. The main reason we use the two-port parameters is that traditional circuit modeling at high frequencies will fail due to parasitic and transmission line effects. So if this network is being run at super high frequencies, our KVL and KCL is not going to hold. So what we'll do is we'll measure these port parameters, these impedance parameters. They'll actually be measured, and this relationship at fixed frequencies will always be true. So we measure, typically we'll measure this, and then these relationships here will still be true. So these values may change depending on what frequency you measure at, but this overall relationship remains true. So we use these two-port parameters to use measured quantities to relate the voltage and the current in this case.